axis, right? If I've got, let's say, Sun, Earth, right? The distance between them, R, and I'm looking for what's the force of gravity. Well, I mean, that's flow chug through, right? There's no problems with that. Pretty easy. Yeah? Okay, I mean, that's just flow chugging to the equation. Fg equals constant m1 m2 divided by r squared. I gave you everything on the right side. You show now the force of gravity. Yes? We label it R as in a radius lots of times because things in gravitational fields, they're being attracted, right? But do you find things lots of times flying inwards? No. Lots of times you find things doing what in gravity? Orbiting, right? Below centrifugal force. Right. These next two units are going to link in. These next three little things are going to link in perfectly with centrifugal force. So we use R, radius that it's orbiting in. Okay, so there's going to be a tie there. Before I get to those type of problems, though, let me set up another type of problem here for you. And I'm just going to use some random masses, and we're going to calculate forces here. So let's say I've got a planet here, planet X, with a mass of I don't know, 2.4 times 10 to the 21st kilograms. Okay? And that's nice and all. There are two other planets close by. There's one other planet, let's say in particular over here, planet Y, with a mass of 3.2 times 10 to the 21st kilograms. And then right about here, there's a moon. Right about there's a little moon. Okay? Just a little bitty guy. He has a mass of 7.9 times 10 to the 18 kilograms. Distance here between, this is going to have a distance r equals 5,960 kilometers. It's actually really short, but just for argument's sake, we're going to deal with that. And this is going to have a distance r equals 9,652 kilometers. And I want to know what's the force of gravity on that moon? What's the force of gravity on that moon? Now, the moon is directly between them, right? X pulls in one way, Y pulls to the other. So what does that logically tell you you're going to need to do? Add vectors. Or here, you don't even have to think of it as vectors. You can just subtract. Yeah, bigger minus smaller, right? Bigger minus smaller. So let's calculate what the force of gravity is from X on the moon. Fg from X is going to equal big G, and I'm going to need you all to punch numbers into the calculator for me here. Big G times mass of X was 2.4 times 10 to the 21st. Times the mass of the moon, 7.9, times 10 to the 18th. Divided by the distance between them. Did you get G, Reed? I didn't. Okay. 6.67 times 10 to the negative 11. So it is. And the distance between them is 5,960 kilometers. What does kilo mean? 10 to the what? 10 to the third, so I'm not going to worry about converting. I'm just going to write that in here. 50960 times 10 to the third, because the calculator will do the conversions for me. Fg of x equals. I'll go ahead and start setting up y while you're doing that. You got it. What's x? 2.12 times 10 to the 23rd newtons. Pretty large, pretty large. But considering we're dealing with planets, that doesn't necessarily translate to a large acceleration, right? Because force divided by mass gives you acceleration, right? That equals mh. Just to give you an idea of the acceleration here. Actually, our acceleration is going to line up to be pretty big. Divide this by the mass of the moon, you figure out the moon's acceleration now. Anyway, and so y is going to be basically the exact same thing. Fg of y equals whatever my g is times the mass of y. 3.2 times 10 to the 21st times the mass of the moon. I'm going to run out of space here. 7.9 times 10 to the 18th. Yes.
On the force of gravity, it's actually times 10 to the 20.
This is times 10 to the 20th. That would make a little bit more sense. That would be a lot less than the acceleration. Still pretty high, though, acceleration. Still over 100. Let's see, 9,642 times 10 to the third. So check out my math there. Make sure you see what I'm doing. I'm just plugging and chugging. Okay, get the forces of gravity from each planet on that ship. Okay.
Are you sure? Because I thought 23.
It is 23?
If you divide by 5960, 5960 times 10 to the third, you have to convert it to meters because you have a kilometer solution.
I did exactly what you were.
You got times 10 to the third in there? All right, I got popular. Let's go with popular vote.
I got 23 for the second.
How many of you get 23? Raise your hand. 1, 2. The rest of you aren't punching it in. Start punching it in.
I did this one.
I'll get an FG as well. We are settled on 23rd. Now, give me the Y, please. $1.75 times 10 to the 23rd. That's true, and I did one heck of a problem. I did one heck of a job setting this up out of the top of my head. Generally, my numbers come way off each other. Everybody double check that. That's what you got, Andrew?
Well, you're using the same power.
Yeah, so it should be 23rd. Yeah, we all good? Okay, cool. Now, looking back on my picture here, that means I've got two vectors here. I've got a vector for x pulling on the moon, coming back that way, right? Equal to 2.12 times 10 to the 23rd newtons. I got a vector y, or a vector from y, and it's pulling on the moon back towards y here of 1.75 times 10 to the 23rd. So what can you tell me is the net force of gravity? Sum of forces, if you will. What is the net force on the moon going to be equal to? Yeah, subtract the two, right? I've got 2.12 times 10 to the 23rd. You can't forget your times 10 to the 23rd, though, by the way. Minus your 1.75 times 10 to the 23rd. So Fg equals what times 10 to the 23rd? 3.37? 0.37?
3.7 to the 27.
0.37 times 10 to the 23rd here. Right, you can convert that if you'd like. Mark.
The radius wasn't square.
Ah, thank you. I have a math error in here. Good. Squared. Let's go back and let's redo all of it. Squared. This is going to make the acceleration a lot more reasonable. Squared. Thank you, Mark. Shame on the rest of you for not catching my math error. All right, I'm going to blame it all on you. So now square, make sure you use parentheses, square it, give me those numbers again. going back and fixing the math there, 1.75 times 10 to the 16th newtons. I need a direction. Remember, force is a vector. That's a magnitude. What direction is this thing going? Yeah, towards x. So that works. Okay. Towards x. That'll be just fine. Now that's when everything's on a nice little line there, and everything's distributed perfectly linear in a linear manner. That's not always happening, right? How often does a move perfectly between two planets that are close to each other? Yeah, not very. In fact, it's only one time out of all the cycles the planets orbiting each other, the moon's orbiting. Apparently, the moon would be orbiting X, right? In some sort of elliptical shape here, but not often are you going to find this perfectly lined up idea. More likely, you're going to find the moon off to the side. Do I need to pause on this so people can copy? We got it now. Good? All right, let me set up another one, right? Here, I've got planet X. Let's try to keep the mass the same. What's the mass of planet X, please?
No, 2.4 times 10 to the
2.4 times 10 to the 21st kilograms, right? And Y now is going to be down here. Its mass was, give me that please, 3.2 times 10 to the 21st kilograms. And I'm going to put Mr. Moon over here. The moon had a mass of 18 kilograms. Now let's give you some distances. R here is going to equal the distance between X and Y. Is going to end up equal 5,110. That should be in kilometers there. Distance from X to the moon is going to be 7. Let's make that small. Let's make this 4,120 kilometers, right? Let me go ahead and help you out here by drawing that in and pointing out that this is going to be a right angle there. Find for me, if you will, the net gravitational force on the moon. Let's find the net gravitational force on the moon. Just an idea for you how to do this. All right, turn you loose. So you got two vectors. You got the force of gravity from X pulling like that. Right, by the way, what angle is the force of gravity from X pulling it? What angle is directly to the left? 180, right? And then find the force of gravity from Y pulling down like that, okay? You're going to need to figure out what that angle is right there. 180 plus that angle will give you the force of gravity for Y. By the way, how would I figure out the magnitudes of these vectors? How do I figure out what force of gravity from X actually is? Yeah, using our equation. Force of gravity equals G m1 m2 divided by r squared. Right, so that gives me the magnitude, and I know the angle for FGX. It's going to be 180. Same thing to figure out the magnitude of FGY. Mass of Y, mass of moon divided by the radius between, I don't have the radius. Where can I get the radius from? Pythagorean theorem, you got two sides of a right triangle. Pythagorean theorem, you get the hypotenuse of that right triangle. Okay? Yeah, you have the from X to the moon and from Y to X. Alright, good. So you have two sides. Figure out the hypotenuse of it. How can I figure out that theta up there so that I can figure out, so I can put it in an angle with FGY? You can do anything, right? You've got hypotenuse, you've got all three sides, right? So you can do any of them to figure out what theta is, 180 plus that theta is going to get you to the angle that you need. Add those vectors. So go for it.